Hi, my name is Elmer Roderick Niembul, and I'm going to talk to you today about how the biomimicry of neurobiological concepts can be used in database normalization. This presentation is a continuation of a previous presentation titled neurUL as a Programming Language, which discussed from a high level how the exploratory open source project neurUL can be used as a programming language. Dirty data is defined as customer or business information that is corrupt, missing, duplicated, or inaccurate. According to the Harvard Business Review in 2016, bad data costs $3 trillion annually in the US alone. According to the UK government, experts think that organizations spend between 10 to 30% of revenue on handling data quality issues. To understand one of the causes of dirty data, let's go through a few fundamental concepts. First of which is software architecture. Software architecture is defined as the shared understanding that expert developers have of the system design. For simplicity, let's focus on one specific type called three-tier architectures. A three-tier architecture is a well-established software application architecture that organizes applications into three logical and physical computing tiers: the presentation tier, the logic tier, and the data tier. The presentation tier contains components that enable user interaction. The logic tier, also known as the application tier, contains components that process information collected from the presentation tier. The data tier contains components that enable the storage and persistence of information processed by the application tier across application sessions. It may contain a database or file, which is the actual data persistence mechanism, and a type of data converter, which is used to convert or map logic tier data components, known as objects, to and from a database or a file. The type of data converter used depends on whether the data being stored is structured or semi-structured. Structured data that can be stored in tables can use object relational mappers. On the other hand, semi-structured data, or data that has no predefined data model, can use serializers, such as JSON serializers and XML serializers, that generate JSON and XML data, respectively. Structured data is typically stored in relational databases. These consist of schemas which define tables as well as relevant columns. Contained data are stored in the rows of these tables, which represent individual records. Introduced in 1970, database normalization is defined as the process of organizing a database, including creating tables and establishing relationships between them, to make a database more flexible by eliminating redundancy and inconsistent dependencies, and ultimately enhance data integrity. It consists of multiple stages, also known as normal forms, which start by eliminating non-simple domains from all relations. For example, in the table shown, we have columns containing simple domains or atomic data, such as ID, name, creation timestamp, and last modification timestamp. On the other hand, the column messages is a non-simple domain as it contains compound data represented by multiple messages within each row. To transform this table so that it complies with the first normal form, we create another table called messages, wherein we insert the primary key from the parent table and transfer the non-simple domain messages as four separate records with the corresponding columns. Then, in the parent table, we remove the transferred messages column, resulting in the normalized avatar table above and the new message table below. As we can see, both tables now contain only simple domains and are therefore compliant with the first normal form. Subsequent normal forms, for example, second normal form, third normal form, and so on, can then be used to normalize the database even further. There are several benefits to normalization. Like having a lean and fit body, normalization ensures a database is properly organized and easily understandable, enabling agility in terms of analysis, processing, and adaptability. In addition, data redundancy is reduced. Consequently, number one, ensuring data consistency as anomalies are avoided. Number two, improving security as insecure duplicate data are minimized. And number three, reducing cost as duplicate data also consumes resources. Despite its effectiveness and utility since it was introduced more than half a century ago, unavoidable redundancies have still been observed. For example, at the schema level, We can observe redundancies in the column definitions, namely the creation timestamp and the last modification timestamp, which are repeatedly defined in both the avatar and message tables. At the data level, in the same individual rows but in different columns, in the same column but in different rows, and in different rows in different tables. Relational databases are still widely used today. However, evidently, even though normalization can be used to minimize and reduce redundancy, left unchecked and considering widespread usage as dedicated sources of truth, unavoidable redundancies can and will grow, resulting in globally persistent, compromised data integrity and resource wastage. As discussed in the previous presentation, the neuralizer uses the following concepts from computer science, neuroscience, philosophy, and linguistics. To serve as a data converter, which accepts objects from the logic tier, to generate simulations of biological neural networks for data persistence. In the results shown at the schema level, both tables message and avatar refer to the same columns, last modification timestamp, and creation timestamp. At the data level, different columns, last modification timestamp and creation timestamp of the same row refer to the same value. Different rows with the same column refer to the same value. Lastly, different rows from different columns of different tables refer to the same value. Using biomimicry, schema and data redundancy can be reduced if not completely prevented, leading to systems that are duplicate-free and efficient. This can benefit systems such as file systems, logs, news, social media, communications platforms, and IoT hubs. A limitation of the presented neuralization process only included column data type and name. Other column attributes were not simulated but should process in the same way. The presented tests focused on qualitative differences, i.e. duplicate prevention. Future tests can also quantitatively compare actual data size of a relational database to a neuralized graph database with the same data. In conclusion, a neurobiologically inspired database language can enhance database normalization to further minimize, if not completely prevent, data redundancy. Here are some references, and thank you.